From the pharmaceutical to the cosmetic to the agricultural industry, the market has started taking a more environmentally friendly approach for the manufacturing of a variety of products. Among the new eco-friendly proposals, the leverage of Bacillus species has gained popularity, as they have been studied to produce extracellular biopolymers known as exopolysaccharides. These polymers are found in bacterial biofilms and have been studied to have a wide range of properties. Specifically, exopolysaccharides of the genus Bacillus have shown capable of emulsification, heavy metal chelation, immunodulation, and biofolucation. Hence, the objective of this initial investigation was the proposal a productive and effective purification strategy of bacterial exopolysaccharides.
Our proposal compromises with sustainability. Hence, we aim to positively impact the spheres of economics, social, and environment. First off, this proposal will benefit societies, as the production of biofertilizers allows for safer food production, may protect farmers' health by abstaining them from using chemicals, and can help develop regions by offering sustainable alternatives. Economic-wise, exopolysaccharides can increase crop yield sustainably, leading to a boost of local economies. Furthermore, the exopolysaccharides market is experiencing a significant growth due to an increase in demand from functional foods, bioplastics, and other applications. Hence, our proposal could help start satiating such demand. Additionally, the optimization of the process could lead to a more cost-effective product, which proves helpful for both the buyer and the industry. Finally, the leverage of organic species and their products help mitigate climate impact, decrease inorganic waste production, reduce chemical dependency, and overall improve soil health.
To ensure quality and the safety of both the process and the final product, it must adhere to these ethical considerations. NOM 010 establishes the guidelines of exposure to chemical agents. NOM 232 regulates the use of microbial pesticides. And NOM 52 regulates the classification and management of waste generated by microorganisms. The process starts in a seed reactor where the inoculum is prepared and then transferred into a 2,000-liter main reactor. The inoculum is 10% of the reactor's capacity. And once the fermentation is over, the broth is then transferred to centrifugation to separate the biomass, which is bacillus, from the cell-free supernatant that contains the exopolysaccharides. The biomass is then freeze-dried for its storage while the EPS undergoes ultrafiltration, where the retentate is kept and then precipitated with ethanol to obtain the exopolysaccharides. The ethanol is then decanted and centrifugated, where dirty ethanol is waste, and the pellet, which contains the EPS, undergoes resuspension with milky water, and then it goes diafiltration to remove the salts. Finally, the EPSs are dried, and then powdered EPS are the final product.
We use a bioreactor for our fermentation and use a stoichiometric parameter to calculate the yield of that reaction. The temperature that we used was 36 Celsius through a fermentation process of 36 hours and a volume of 1900 liters.
The complex media formulated for the Bacillus species was the following, where the main components highlighted are glucose as a main carbon source and yeast extracts for satiating nitrogen demands. Additionally, an antifoam was added to prevent excessive foaming. All the concentrations were chosen according to the species demands, while also considering that too high concentrations of certain components, such as glucose, could cause growth inhibition.
Now, regarding the results, both biomass and EPS recoveries were high with 94.1 and 77.9% respectively. For the yields of the fermenter, we calculated 0.33 kilograms of biomass per kilogram of substrate and zero point 0.3 kilograms of EPS per kilogram of substrate. Finally, at the end, we achieved a purity of 99.97% and a final production of 77.9 kilograms of EPS per batch. For the economical analysis, due to the very high degree of purity and based on certain sources, we set the selling price at $3,200 per kilogram, while the biomass could sell for $150 per kilogram. The total investment for this operation is a bit over $37,000 with an operating cost of less than $15,000 per year. Finally, our gross margin is 72.5% with a return of investment of 88.6% and a payback time of over a year. What we can conclude is that this proposal is feasible with the right market being considered. Highly pure EPS is a product only used in research, and this available market at much higher prices is smaller than the agricultural sector, in which the EPS doesn't require such high levels of purity to become an appealing product to buyers. Hence, reducing the purity is a feasible alternative.
And lastly, while our product is economically profitable, it is highly priced for our main markets. The sheer purity of the product justifies it, but the market won't be able to pay those prices. From that purity, we can sell to other sectors, such as education, research, where our products are actually lower than the average. So the options are changing the target markets or lowering the quality of our product for lower prices.
Finally, due to the agricultural applications of the products, purity can be sacrificed to reduce the production costs and make the process more economically feasible. This can be done by substituting the resuspension in milky water for normal water, and more exopolysaccharides can be obtained by diluting the broth after the fermentation to avoid the biomass sequestering the EPSs during the first centrifugation.
To conclude, I would personally omit the diafiltration step. The reason behind this is that the purity obtained with the current process is enough for pharmaceutical or cosmetic formulations. By reducing the purity percentage, we would still be obtaining a product pure enough for biofertilizers, while also reducing production time, resource demand, and operation cost.